Okay, today we're going to look at chapter 2, which is all about motion. So, in chapter 2, we actually really start getting into physics. So basically, we're going to be looking at those basic principles that describe how the universe works. We're going to be looking at matter, motion, force, and energy. Now, motion's everywhere. We do motion every day, every minute of the day. Okay, so in this chapter, what we're going to focus on is speed, velocity, and acceleration. Now, there are two types of motion. There are straight line motion and circular motion. So straight line motion, I'm going from point A to point B in that straight line. I'm not going to deviate from that straight line. Whereas circular motion, I'm going around in a circle. Okay, the Earth going around the sun is a circular motion. Now, in order to define motion, we have to look at the position. We have to look at that location of that particular object. So it's important that there is a reference point and a measurement scale. So we're able to define that position of an object. Now, if something's in motion, it's continually changing its position. So when you start to describe motion, you're describing motion as the time rate of change of position. So basically, you have a combination of length and a combination of time to describe motion. Now, we look at speed and velocity. So speed and velocity in the physical science, they're going to have distinct meaning. You will catch me saying speed and velocity interchangeably because I know the difference in my head, and you will get to know the difference and probably do the same thing. So the main difference lies with these two words, scalar and vector. So speed is a scalar quantity, which means it only has magnitude. So if you look at the example I have written down there, a car is going 80 kilometers per hour. Well, 80 kilometers per hour is its magnitude. But when I look at that, I have no way of knowing 80 kilometers per hour where? To the north, to the east, to the south, to the west? I don't know. And that's because that's speed, the scalar quantity. Whereas velocity, being a vector quantity, is going to have both magnitude and direction. So when I look at the statement under the velocity bullet point, notice I've added north at the end of 80 kilometers per hour. So now I not only know my magnitude, but I also know the direction that that particular object is traveling. Now, vectors are usually represented by lines and arrowheads. So the length of the line is what's proportional to the magnitude. The arrowhead is what's giving you your direction. So you can see on the first line, both arrowheads are pointing toward the east. So you're going 80 kilometers per hour toward the east. You're going 40 kilometers per hour toward the east. Notice the 80 kilometer per hour line is much longer than the 40 kilometers. The bottom line, the examples, notice the arrowheads are pointing toward the west. And notice we put a negative sign in front of it to show that they are pointing toward the west, toward the negative side of that number line. So negative 40 kilometers toward the west, negative 80 kilometers toward the west. And this is a little picture that shows you how comparing the red car to the blue car. Notice the red car is moving toward the left, the blue car is moving toward the right. So, like we saw in the previous example, your vectors can either be positive or negative depending on the direction they're going, whether they're going left, right, up, or down. And they get that positive and negative notation from the number line. So speed is distance over time. So we use a lowercase v to denote speed, and the d for distance, the t for time. Notice because it's average, we put this little line over the v. Okay. Now, speed being distance traveled, sometimes you might also see v equals delta d over delta t. So the delta, that little triangle symbol, means a change. So that change over that entire interval. Now that delta symbol is never independent of the d, okay? Meaning that simply means a change in distance over a change in time. So the distance we're talking about here is the actual path that it takes from point A to point B where it comes to stop. Okay. Now sometimes we don't want to know the average speed. We just want to know the instantaneous speed. And that's going to be the speed of an object at an instant in time. So that delta t, that time interval, tends to be very small. So for instance, your instantaneous speed, you're driving a car, you glance at your speedometer, that is your instantaneous speed. That is not your speed over a time interval. So police are using a radar gun. They will clock your speed at that precise instant in time. And you can see here's a picture of our speedometer showing instantaneous speed. Now the only difference between speed and velocity is the different quantities, scalar versus vector. Okay? So your average velocity is going to equal displacement over time. Notice it's displacement, not total distance. So your displacement is going to be the distance between that initial and that final position. Naturally, your direction would be toward the final position. Just like we had instantaneous speed, we can also have instantaneous velocity. So this picture right here shows you the difference between displacement and distance. So notice that displacement is going to be your vector quantity. Okay, and notice displacement is starting out at this dot around your hometown, and it's going straight to the dot by State University. Displacement doesn't care if you took all kind of twists and turns and back roads or whatever to get to point A to from point A to point B. It just cares about your initial position and your final position. Whereas distance, you would have to add up all the distance along that brown path that you see in this picture, okay? Because you're looking at actual path taken as opposed to just that vector quantity between those 2 points. So in this example that your PowerPoints have worked out, you're asked to describe the speed of the car above. And with this picture, you can tell that you've gone a distance of 80 meters. We have 20, 40, 60, 80. So total distance is going to be 80. And total time, we're ending up with a time of 4 seconds. Okay, so speed is, V is distance over time. So we're going to put our 80 meters on top of our 4 seconds, divide it out, and you should get 20 meters per second as the average speed. Now, if I wanted to make this into velocity, the only thing I'm missing is direction. Well, here it's obvious that my car is moving toward the east. So all I would have to do is to turn this example into velocity is basically write the car speed is 20 meters per second east. And that becomes my velocity instead of my speed. This next example, you're asked for how far would the car travel in 10 seconds. So here, we're looking at how far. So basically, you're looking for distance because you're asked for how far. Now, from the previous example, we know that our velocity, our speed, was 20 meters per second. Okay? And we can see from the picture, our time is 4 seconds. Remember, it helps to solve problems if you make your list. Notice in my list, I put what I'm looking for, a question mark, and then I put all the pieces that I'm given with the correct variables. So I know my basic equation is speed is distance over time. I'm asked to solve for distance, so I need distance by itself. So what I'm going to do is multiply both sides by time. So on my right, my time's going to cancel, which will give me my equation, distance equals time times the speed. Okay. So all I'm doing is taking my 20 meters per second, multiplying it by 10, and I get 200 meters. Okay, this ends part 1 of chapter 2's video.